Good evening, everyone. Welcome back to MPL Live Session. So today we are at week 4 and we will be discussing all the lectures that have been taken in week 4. That would be more or less completing the chirality with introduction of polarization, polarized light, circle, polarized light, and certain concepts of absorbance. So we will wait for a few minutes for others to join. And if there is any question regarding what we have discussed in last week, any query regarding the assignment problem, you can just unmute yourself and ask me directly, or you can put your question in the chat box before we enter into the week 4 session. Okay, so we can start now. So here are some questions that means assignment problems that would be useful for you to solve the actual assignment which has been given at the end of the week 4 session. So this we will be talking about at the end of the lecture or as in when we are done with the discussion of basic concepts. So here are the topics that have to be covered in this session. We will be talking about the chirality and chiral environment. So this is the website that I'm showing over here. You can go and check this website where you can easily see these points, plain polarized light and optical radiation. This is an animation website where you will be able to see how it actually works in 3D environment. So let's get started with our first topic, which is chirality and chiral environment. So we have already talked about it in our previous sessions that what is a chiral molecule, which is when produces non-superimposable mirror images. So for a chiral molecule, the one thing that is required, the definition says non-superimposable mirror images. And in this way, we have seen, like if we have to talk about the molecules with point groups, which are chiral, so they come in a category of CN or DN. Exception that we have is open the H2O2. It is C2.0, but it is not chiral. The reason we have already talked about. The reason is free single bond rotation, which cancel out its chirality. Okay, so this we have studied in our last session. What we are basically trying to do today is, so chirality is basically, it is a key tool for biological systems. Why is it so? Because it helps in molecular recognition. This is very important concept and it works on lock and key mechanism, which we have already discussed earlier. Like there is one key for one lock. Similarly, chirality, the molecule having a chirality that can only be recognized in a one chiral environment. So it helps in molecular recognition. So how it can be detected? It can be detected only by a chiral environment. So we know that chirality will produce enantiomers, and these are the isomers which have similar physical and chemical properties, but they differ in their rotation. So let's say we have enantiomer enantiomer A and enantiomer B. So they can only be distinguished by chirality, as you have already mentioned. Say, for example, you have a synthetic, you have synthesized a product. This product is having 50% of enantiomer A plus 50% of enantiomer B. So when both the components, both the enantiomers are present at the same time with equal proportion, then there is no axis. This is called 0% enantiomeric axis. When both the parts are present equally in equal amounts, then there is no isomer which is present in axis. So therefore, it is called 0% enantiomeric axis, and hence this makes your product achiral. So then your product, even if it is having enantiomer, still your total product becomes as a totality. If we count it as, it becomes achiral because your both the enantiomers having A and B, they are present in 50-50 proportion. Only What we can do to make it chiral, so if we add chiral acid, say for example it reacts with acid and we add chiral acid, then we can get one enantiomer in axis over other. So this here we can talk about the enantiomer axis. So here we have seen that first topic that was of chiral and chiral environment and enantiomeric axis has been taken care of. Since we were talking about in our last class many amino acids, those were 20 amino acids, alpha amino. But besides that, there are some other amino acids as well that are present in nature. We have when if this is your alpha group, this is from your beta. So this is the secondary chiral center. It is called isoserine because in serine we were having ROCH2H, and similarly it is having some derivatives where if we are taking this NH2 COH, now this is alpha carbon and this is called homoserine. Okay, some other more examples. NH2 OH. Now this center again is chiral. This is 4 amino 2 hydroxy butyric acid, as the numbering has started from 1, 2, 3, and 4. So the name that is being given to it is 4A2HB8. This is its 4. Second we have is NH2 OH COH. Now this is our chiral path. Now again, if we talk about this is 1, 2, 3, and 4. So the name is 4 amino 3 hydroxy. Earlier was 2 hydroxy butyric acid, and the code is being given as 4A3HPA. So you have to be very careful which code you are taking and which code you are talking about. One last example that we can take from different amino acids is we have COH, NH2 group, and another COH. So this becomes a chiral center, which is called beta amino methyl, this whole group, succinate acid. This is your alpha part. This is your beta, and beta is having CH2NH2. That's why beta amino methyl succinate acid. So this is another example so that we have taken into picture. Now we will move to our next topic is light matter interaction. In our first session, we have talked about symmetry with energy, with mathematics, with matter. Symmetry with other things are also there. So our next topic is light matter interaction. So each and everything is highly correlated with the main concept of sulfur dichroism, which you will be eventually knowing it. So what we know that when we have the ground state and excited state, which is having energy difference of E, and if we suppose that there is one electron in the ground state and we are shining the light onto this particular, so this is your light which you are shining onto the electron. This is your electron. And now what will happen? It will go to the excited state. So what equation does it really use? So it uses as H psi equals to E psi, which is your Hamiltonian. Psi is your wave function. E is your energy. And this equation is known as Schrodinger wave equation. Actually, Hamiltonian is something, it is approximately we can call as an atmosphere which controls how the electron should move and therefore will define the energy of the system. So since we are shining the light on the electron, now its electron cloud would be perturbed, and with respect to that, how it will move to excited state and what energy it would actually obtain, that defines by the Hamiltonian, which is the wave function. So if we say that for the ground state, your Hamiltonian will be this way, and energy and ground state. And similarly, for the excited state, since the atmosphere is different for the excited state, so Hamiltonian change, so is the function, excited state, and energy also excited state, which means on radiation, perturbation happens and changes the Hamiltonian, and therefore changes the energy. That's why we have written for downstream excited state is different because when it is being radiated, then the electron cloud would get perturbed, and because of the perturbation, there would be a changes in the atmosphere that is your Hamiltonian, and therefore your energy would be changed. That's why on radiation, there occurs a change in energy, and we see a transition from the ground state to the excited state. So the main question is why that light actually affects the electron so much. So the question is, This radiation is nothing but the electromagnetic radiation. Why the electromagnetic radiation affects or interacts with energy density? So actually, to answer this, we know that electromagnetic radiation is composed of two parts. One is electric field, another is magnetic field. And they both are perpendicular to each other always, right? So among the two, electric field vector is very, very dominant compared to the magnetic field. So it affects the electron density. This vector affects the electron density. How? So how does there are two factors with which electric field interacts with electron distribution. First is the strength of the field. How much is the strength? And second, how you will get an alpha value, which is the polarizability. That means the perturbation that it feels. So whenever we are changing the electron distribution, it leads to the distortion in its electron density, and therefore that is called as, this is nothing but the distortion or redistribution or electron density in electron density. So basically, how these two factors are dependent on each other. So there is a term which is equals to both the factors, and this is called as transient dipole moment. So what basically happens when you apply the electric field, it would change or perturb the electron density of that electron, and therefore it feels the distortion, which rises the polarizability. Since it is for that particular moment only, the changes happen instantaneously, so it is a transient moment. It needs not to be permanent. That's why it is called as transient. Now, there is a likely question that what is the probability that actually of electron to go from ground state to the excited state. So we discussed that, okay, when we are radiating the electron, it is humping or hopping to the excited state. But why? Because electromagnetic radiation is comprising of two fields, which is one is electric field and another is magnetic field. Electric field has more value to it. It changes or affects the electron density distribution a lot. How? And therefore it creates a transient dipole moment. But do we really know that there is a probability of going of electron to go from ground state to excited state? So for that, the probability is being given in the form of an equation, and this is equals to minus infinity to plus infinity, the wave function of excited state, the transient dipole moment, and the wave function of ground state, and the beta, which is your volume element, dx dy dz. So if the conditions are if the value is equals to 1, that means transition is allowed. That means there is full probability of having the excitation of the electron to the excited state. And if the value is 0 of this probability, that means transition is not allowed and it will not go to the excited state. It's positive. This is very, very important. So now the follow-up question is, we understood that how it is interacting, how its electron density is getting distorted, then what what factor is actually influencing it to jump from ground state to the excited state. But how do we know that how much interaction is happening? The next question is, how do we know how much interaction between that radiation and the electron is happening? So for that, we have an experiment. So say for example, we have a medium here where we are saying that it is containing electrons or something. Now here we are shining one light, which is having an intensity of I naught, and after that it releases only I. So the transmittance value, that means what we gave and what we observed, T is equals to I by I naught. And absorbance, what actually this sample has, there would be a sample inside which has absorbed. So it is being given as A equals to log of I naught by I, because A is inversely proportional to the transmittance, and that's a logarithm of it. And now this absorbance through interaction is dependent on the absorbance, and absorbance is further being correlated as a absorbance is equals to epsilon C and L, because absorbance is directly proportional to the concentration of your sample. C. It is directly proportional to the length of the cuvette, that is the path length cuvette that is being used, size of the cuvette. Say for example, if we have in A case, the size is this L1, and in other one, the size is L2. L2 is greater than L1, therefore A2 is greater than A1. Followed by third that we have is molar absorption coefficient, which is given as epsilon. So this is basically a coefficient of the molecule. So it's a property of the molecule. So it varies from molecule to molecule. Whereas the concentration and the length are the system properties. So if E value is epsilon value is high, then you will get more. So what is basically this epsilon? So this actually gives an idea of how much electric field. This is the basically factor which gives you an idea of how much electric field is interacting with the electron density redistribution, which we were talking about. Then how do we get to know what amount of interaction is happening between the two, the radiation as well as the electron density? So to understand this, we have a concept where we see that we know that how the electric field oscillates. So electric field oscillates in a sigmoidal fashion. So for example here, so we know it would be having crust and trough going in this direction. So this is the direction of electric field. If it is passing through the electron cloud and we are considering that this is the electron density, so we say that how it will oscillate this way. So therefore, there is a function called oscillatory function, which is given as Eg, where E stands for excited state and G stands for ground state. And this value is equal to 4.315 into 10 to the power minus 9, which is a constant, going from wave number mu1 to wave number mu2, epsilon value mu into derivative of mu. So how much oscillation? So as we said that we were interested in getting to know how much interaction is happening. So epsilon is the one term of molar absorption coefficient, which is a property of the molecule, and that actually dictates how much it is going to interact. And there is one oscillatory function which will give you exact value, which depends upon the base number as well as the molar absorption. Say for example, we have this graph where we are having on the y-axis epsilon value, and here it is at mu1, one wave number, and mu2. So the first that we have is this one, and the second that we are having is this one. So this part which is highlighted in red, and this part which is highlighted in. So this is having more distribution, which is more value of mu to d mu. Therefore, it would be having more oscillatory motion. So area under the curve is epsilon value, which is in the range of mu1 to mu. Lower the epsilon, lower the oscillatory strength, and lower would be the transfer of the motion. Now there are certain things that, so if epsilon is high, then allowed transition. Epsilon is low, then not so allowed transition. Because it would only define the oscillatory motion, and we have certain cases where we have different values of this epsilon. So different cases that we are having. First is if epsilon the first case is pi to pi star, the epsilon is very high. Therefore, it is allowed transition. Its range is approximately 10,000 molar inverse, centimeter inverse, followed by is n to pi star, where we have epsilon is low in the region of 5,000 to 10,000 molar inverse, centimeter inverse. And the third that we have is DD transition, where we know that epsilon is very low. So it is in the range of 1 to 10 molar inverse, centimeter inverse. So it approximately becomes spin forbidden, say in case of Mn plus 2. It's d phi distal, so it's a d to d transition. Therefore, so depending on the epsilon value, you will be knowing how the transition from the ground state electron to excited state would happen. More the epsilon value, more will be the oscillative function, and therefore more probability is there for the electric field to interact with the electron density distribution. So now moving ahead, so generally we know, like we were talking about the light source. So generally we know that whether the white light that we shine, or let's say for example white light we are having, whether it is polarized or not. So basically white light is non-polarized light. It's a combination of the light in all the directions. So white light would be looking like something like this. It is moving up and down, moving diagonally. These arrows are nothing but the direction of the light. So here is the white light. If we pass it to this is a filter, we can say, which absorbs all that all directions except light in one direction. Therefore, we would be getting a plain polarized light. This is called a plain polarized light. So we know that plain polarized light actually helps in detecting chirality. And we know that chirality can only be detected by a chiral environment, right? So therefore, does plain polarized light is plain polarized light having any chirality? That we need to find out. So basically, the plain polarized light that we have shown is upper and lower half. So this is your plain polarized light. It is actually a superposition of two different rotating systems, which are, one is in left side, the other one is in left circularly polarized, right? LCP, and therefore right RCP. So it's a combination of LCP and RCP. So how it actually works, so how it was looking like. So we started with this way, and then when it moves to, you can make a center over here. When it moves to left side, then it comes to center left, then center down, and completely down. So this is your LCP motion, whereas you have started with first here, then here, then here, then here, then here. So this is the maximum that we get here this way. So ultimately we were able to get the plane polarized light, giving a resultant number. This is your RCP. So what if question is, what if RCP and LCP do not move with the same speed? Then how it would look like to an optically active medium? Let's say chiral medium. For example, we take that RCP is greater than LCP in terms of speed. That is, RCP moves faster. If that is the case, then left part would be very less. So it would be not moving faster. This is your center. This has moved faster. So the resultant would be in a direction of the right side. So more towards right, we will see the direction of the right. What really happens is, so RCP is something like this right side interaction, and this is your LCP, RCP light. So when there is a molecule, medium, this is your medium. So when one goes faster, for example, this goes faster and this becomes very slow. So this slows down, this is faster. What happens is one of the two interacts strongly with the medium. Therefore, one moves faster, another slows down. So this is how if they both have different speeds. So how do we talk about the based on the because of the refractive index how it happens? So we have a terminology called optical rotation, which is given by phi, and that is nothing but directly proportional to refractive index of this is your speed and L is it is your refractive index. And we know that it is inversely proportional to the speed. Therefore, if speed of your RCP is greater than LCP, therefore NRR would be less than LNL, and in that case, your phi would be positive, and its actual definition is 180 into L and L minus NR divided by L. Here, L is your path length and lambda is your gradient. So this is all about the week 4 session, which we have taken into consideration. Please take your 5 minutes to go through all the concepts one more time and see if you understood every part of it. We will take a recap one more time if somebody has missed it, and then we can start with our questions. So basically, we are done with our light metal interaction, transient dipole, absorbance, plane polarized light, and optical radiation. So everything has been covered for today. So what we started with the chirality and chiral environment. So the chiral molecule, we have already known that it produces non-superimposable mirror images. The point groups that are called to be chiral, that is CN and DN. An exception that we have read, it doesn't call as exception, but open book structure of H2O. It is basically having C2 point group, but C2 belongs to chiral point groups. Since it is having a free bond O rotation, single bond rotation, so it cancels out the chirality. Therefore, it does not have a chirality, even though it belongs to a chiral point group. Followed by, we were talking about the chirality, which is a key tool for biological systems. It helps in molecular recognition. As we know that it follows a lock and key mechanism. It can be detected only by a chiral environment. So from the chirality, we get enantiomers. Enantiomers are basically having similar physical and chemical properties. So say, for example, if in a product we are having similar proportion of both the enantiomers, 50% as well as 50% B, so there won't be any enantiomer which is more in number, that is in access. So 0% enantiomer access is there. If at this point we add one of the chiral acid and that interacts with one of the enantiomer, the other becomes access over the first one. Therefore, we can have certain enantiomeric access. So in last session, we have discussed about 20 amino acids. And besides that, we have other amino acids as well. As you can see, isoserine, homoserine. Furthermore examples, 4-amino, 2-hydroxy and 3-hydroxy butyric acid. Followed by we have beta-amino methylsuccinic acid. There are many others. When we have understood the concept of chirality and the application in biology and what is the role in molecular recognition, so we need to introduce that how it actually interacts with the metal and how there is an interaction between the light and matter. So we know that if we strike or if we radiate the light or the electromagnetic radiation onto the electron, it would go to the excited state. So basically, how this work happens, we know that Schrodinger wave equation gives us a Hamiltonian into wave function, giving energy into wave function. So this Hamiltonian is nothing but the atmosphere, which controls how your electron should move when it has been affected by the radiation, and that defines the energy of your system. So basically, for the ground state, if we are saying there is Hamiltonian H, and depending on that, wave function is psi ground state, giving you one energy level. For the excited state, there would be different atmosphere. That means Hamiltonian is changed, and so your energy as well. Which means on radiation, the perturbation of the electron density will appear, and therefore it changes the Hamiltonian, correspondingly changing the energy. Now, why electromagnetic radiation actually affects or interacts with your energy density? So basically, electromagnetic radiation is comprised of two fields. One is electric field and other is magnetic field. You know that both of them are perpendicular to each other, having the 90 degrees angle. And in this way, we have electric field component to be affecting the electron density bit more. Magnetic field also does, but that effect we will talk about later. That effect is very minimal, but it is still there. So how the electric field affects the electronic distribution? So basically, when it affects it, so it creates a distortion in the electron density, and therefore, how much it is affecting that depends upon the two factors. One is strength of the electric field, like how more you are giving the electric field, and how much distortion it is facing, that is polarizability. So combining the two factors, we have a transient dipole moment. So as in when electric field interacts with the electron density, it creates polarizability, which therefore, as a combination, creates a transient uh, dipole moment, which needs not to be permanent. Because since it is very simultaneous, as in when the electric field is interacting, the polarizability is happening, and therefore it needs not to be permanent. Now, what is the probability of the electron to go from ground state to the excited state on getting radiated? The probability is given by this following equation, where we have the psi star wave function of electron excited state multiplied by transient dipole moment and wave function of ground state into d tau value, which is the volume element. So the conditions are, if the total value of this probability is 1, then the transition is allowed. If it is 0, then it is forbidden. Now, how do we know how much it is interacting with that particular thing? So how that interaction is occurring, first of all. So we can consider a sample, and we are passing the light with an intensity of I naught through that sample. And what we see a transmitted light as I by I naught. So some part has been absorbed by it, and absorbance has been given as equals to log I naught by I. Now, this absorbance is highly dependent on the concentration of the sample, the path length of that cuvette. If the path length is more, there would be more absorbance, and at last, it is dependent on the epsilon value, which is molar absorption coefficient. So, other two, concentration and the length, they are the system properties which we can vary, but this epsilon is a property of the molecule itself. So, what is epsilon basically? It actually defines that how much electric field is interacting with the electron density redistribution, and based on that, we have an oscillatory function, which will tell you that more the oscillatory function value, more the epsilon value, more interaction is happening. As you can see that more distribution between the nu one and nu two wave numbers, more epsilon values there. If epsilon is higher, then the transition allowance probability is more compared to if it is low. And there are certain cases, if we consider in complexes or some molecules, if there is pi to pi star transition, then the epsilon value is very high. That is 10,000 molar inverse centimeter inverse. So it's highly allowed, followed by n to pi star transition, which is low, but it is allowed. And the third is d to d transition, which is very low as the value of epsilon is very less. And it is generally considered to be spin forbidden until unless there is some other parameter coming into picture. Once we understood that only it is interacting, what is the major factor which would tell you that whether the interaction is going to happen and whether it is going to be excited or not. After that, we know that the light, white light that we are shining, that is not polarized. So if we are having a plain polarized light, and that helps in detecting the chirality, that can only be possible if it is chiral by itself. So do we have a plain polarized light and there is anything, something related to chirality? Yes, plain polarized light is basically a function of two uh, circular polarized light. One is in left direction, another is in right direction. And here is the movement of LCP and RCP. So depending upon its superposition, that becomes a chiral in nature. So if out of the two, one is having moves, or both of them, they don't move through the same speed through an optically active chiral medium, then what will happen? We'll be having a direction in one particular side of the movement. We can understand from here if we have an RCP and LCP light and we have a chiral medium. Now, one of the two lights are interacting with the medium in a more strongly manner. Therefore, uh, one gets faster in movement and other gets slower. And based on that, we have an optical rotation, and that value tells us whether this molecule is positive, plane polarized. Its optical rotation will give you positive or negative value depending upon whether the movement of your RCP and LCP is different, same, or one is greater than the other. So this is what we have understood in this session. Now we will quickly take up the questions. So I will give you 2 to 3 minutes to just revise these concepts, and please, this session is open up for the questions, and please ask me anything if you have not understood so far. Okay, so we can start with our questions. They're pretty straightforward as the concept is very simple. The first question says that you have a chirality, and chirality is a key tool for biology because it helps in molecule synthesis. No. It helps in molecular recognition. Yes, we saw that having a lock-in key mechanism. It helps in disintegrating molecule. No. So only the option B is correct. Followed by second question is, for a transition to be allowed, the value of the transient dipole moment should be, we know the transient dipole moment is given by minus infinity to plus infinity, psi star, excited state, and the transient dipole moment. Then d tau, it is actually not the value of transient dipole moment, it is the probability has to be, anyway, makes sense. It has to be 1, so option C. If it is 0, then it is not allowed and other values are not possible. Absorption of the substance, as we know that it is equal to epsilon C into L. So it depends upon the concentration, it depends upon path length, it depends upon the molar absorbance. Therefore, option D is correct because it contains all of the above. Followed by right, the decreasing order of molar absorption coefficient epsilon value for these transitions. So we have already discussed. So pi to pi star is greater than n to pi star, and followed by DD transition. We know the values. It is around 10,000. It is around 5,000 to 10,000. And this is 1 to 10 molar inverse, centimeter inverse. Values are not much important, but if there's a question, then you should be able to answer it. So the following statements are true about a plane polarized light. It is a monochromatic source, yes. It is chiral actually because of the RCP and LCP, which makes it a chiral. as they both move in a different direction. So option A and B, followed by if the left circularly polarized light moves faster compared to the right one, then the optical rotation will happen in which direction? So we know that LCP is greater than RCP, therefore it would be in the left direction. So option is B. Given a path length has been given 1 dm, NL is equals to NR, and lambda has been given. Optical rotation value has to be find out. We know phi is equals to 180 into L and L minus NR divided by lambda. If you put the values, you'll get it. But since it has been given NL equals to NR, so therefore this value becomes 0, and therefore phi is equals to 0. You don't have to worry about anything. So these are certain examples that would help you to solve the assignment problems of your week 4. Please do let me know if you have any doubts or questions. We have still another 15 minutes, and if there is any doubt that you want me to discuss on, please let me know. Thank you.